Good afternoon, my name is Arash Tavakoli and I'm a PhD student at Imperial College London. Regretfully, I cannot be there in person, but I've made this presentation in hopes that it makes up for my absence.
In this talk, I will describe a novel neural architecture which enables the application of discrete-action reinforcement learning algorithms to domains with high-dimensional discrete or continuous action spaces. This work is done in collaboration with Fabio Pardo and our advisor Petar Kormushev. The motivation behind this work is that discrete-action algorithms, most notably the deep Q-networks or DQN for short, have been central to numerous recent successes of deep reinforcement learning. For instance, DQN-based agents provide a state-of-the-art performance in the Atari 2600 benchmark, both in terms of sample efficiency and final score. Mainly, this is due to the off-policy nature of deep Q learning, as well as the many extensions that improve upon its speed and stability. Despite the remarkable performance of deep Q learning in domains with low-dimensional action spaces, such as the Atari benchmark, its application to domains with high-dimensional, discrete or continuous action spaces is currently considered intractable. In fact, while there are numerous alternative solutions for tackling continuous action domains such as the proximal policy optimization, there is currently no generic tractable method for large high-dimensional discrete action problems. The problem here is that the number of possible actions increases exponentially with increasing action dimensionality. As a result, the main issue that arises is that such large action spaces are difficult to explore efficiently. Furthermore, the training of large networks that explicitly represent a combinatorial set of actions easily becomes computationally expensive. We propose a neural network architecture which distributes the representation of the action controllers across individual network branches, meanwhile maintaining a shared network module among them to encode a latent representation of the input. Specifically, each action branch is merely concerned with controlling an individual degree of freedom, for instance a robotic joint. At every time step, the selected sub-actions across the branches are concatenated to form a joint action tuple for interaction with the environment at that time step. The key insight behind the proposed architecture is that for solving problems in multidimensional action spaces, it is possible to optimize for each action dimension with a degree of independence. This can potentially enable the linear increase of the number of required network outputs as opposed to the combinatorial increase in the current discrete action algorithms. It is well known that in fully cooperative settings, the parallel distribution of the policy across several independent learners is subject to miscoordination. This, in principle, leads to convergence problems. We hypothesize that maintaining a shared network module paired with an appropriate training procedure can play a significant role in coordinating the semi-independent action branches and therefore achieve training stability and convergence to good policies. We believe this is due to the rich features in the shared network that is trained via the backpropagation of the gradients originating from all the branches. We verify our hypothesis through an ablation study by evaluating the performance of an action branching agent with and without the shared network module on numerous domains with increasing action dimensionality. The empirical results show that the proposed action branching agent with the shared network module scales gracefully to environments with increasing action dimensionality, while the one without the shared network module immediately deteriorates with increasing action dimensionality, indeed, as a consequence of independent learning. This indicates the significance of the shared network module in coordinating the distributed action branches and thus verifies our hypothesis. Next, I will describe the action branching agent that we designed for our study and summarize the results of our experiments. We designed a proof of concept agent called Branching Dueling Q-Network, or BDQ for short, that is based on the incorporation of the proposed action branching architecture into the DQN algorithm, as well as adapting a selection of its extensions, double Q learning, dueling network architectures, and the prioritized experience replay. The figure illustrates the specific action branching network architecture implemented for the proposed BDQ agent. As demonstrated here, when a state is provided at the input, the shared network module computes a latent representation that is then used for evaluation of the common state value and the distributed action advantages. The state value and the distributed advantages are then combined via a special aggregating layer to output the Q values for all sub-actions and across all action dimensions. These Q values are required for training the network. For acting, the distributed advantages on the action branches are sufficient to select the sub-actions across all action dimensions. Now I will describe the methods that we used in our BDQ agent for incorporating DQN and its extensions into our action branching architecture. As described earlier, BDQ uses a common state value estimator for all action branches. This can be thought of as the incorporation of the dueling network architecture into the action branching architecture. As highlighted in the figure, for an input state S, the state value branch provides an estimate of the common state value V of S, and each action branch D provides a state-dependent advantage estimate A sub D for each of its sub-actions U sub D. To produce an estimate of the Q value of each sub-action U sub D, the advantage of the sub-action U sub D needs to be aggregated with the common state value V of S. Most simply, this can be done by adding the state value V of S to the advantage of each sub-action. We experimented with several aggregation methods, and our best performing method is to locally subtract each branch's mean advantage from its sub-action advantages prior to their summation with the state value. We tried several different methods for generating the temporal difference or TD targets for the DQN updates. A simple approach is to calculate a TD target similar to that in double DQN for each individual action dimension separately. In practice, we found that having a global learning target for all action branches achieves better performance. One such target, and our best performing one, is the average of the double DQN based TD targets across all action branches. We just saw how the TD targets are generated for each action branch. Now I describe how the TD errors for multiple action branches can be combined together to produce a unified loss at every training time step. To preserve the magnitude of the individual errors, the loss can be specified as a function of the sum of the absolute TD errors across the branches. In practice, we found that defining the loss to be the mean squared TD error across the branches mightily enhance the performance of BDQ. Furthermore, to adapt the prioritized experience replay into the action branching architecture, we need to produce a unified TD error to be used for calculating a transition's priority. To reflect the magnitudes of the individual TD errors across the branches, we specify the unified prioritization error to be the sum across a transition's absolute distributed TD errors. We evaluated the performance of the proposed BDQ agent on several challenging physical continuous control domains of varying action dimensionality and complexity. We begin by comparing the performance of BDQ against its standard non-branching variant, the prioritized Dueling Double DQN, or Dueling DDQN for short, on a set of physical manipulation tasks with action dimensionalities 3, 4, and 5 degrees of freedom. For each task, we consider 2 discretization resolutions resulting in 5 and 9 sub-actions per joint. As can be seen in the learning curve plot on the left, in the low-dimensional reaching task with 3 degrees of freedom, both branching and non-branching agents perform similarly. In the next task with 4 degrees of freedom, the standard Dueling DDQN agent with 9 sub-actions per joint is significantly less sample efficient than its BDQ counterpart. In the high-dimensional reaching task with 5 degrees of freedom, we see that the Dueling DDQN agent with 5 sub-actions per joint starts to perform relatively poorly. For this task, we were unable to run the Dueling DDQN agent with 9 sub-actions per joint, as running it was computationally expensive, having to explicitly represent approximately 60,000 network outputs. In all tasks, BDQ performs well and converges to good policies with robustness against the discretization granularity and action dimensionality. To verify our hypothesis regarding the significance of the shared network module in coordinating the distributed action branches, we compare the performance of BDQ against the variant without the shared part. We refer to this agent as Independent Dueling Q-Network, or IDQ for short. We evaluated the performances of both BDQ and IDQ on a set of standard continuous control benchmark domains from the OpenAI's Mojoko Gym collection. The results show that the performance of IDQ, shown in red, quickly deteriorates with increasing action dimensionality. In particular, going from the reacher domain with 2 joints to the hopper domain with 3 joints renders the IDQ agent ineffective. This is while BDQ continues to perform well across all tasks and converges to good policies. Our ablation study comparing BDQ against IDQ verifies the significance of the shared network module in coordinating the distributed action branches. Additionally, by comparing the performance of BDQ for discretization resolution 17 and 33 sub-actions per joint, we see that despite the significant difference in the resulting total number of possible actions, BDQ continues to learn efficiently and converges to similar final performance levels. Lastly, we compare the performance of BDQ against the state-of-the-art continuous action algorithm, the Deep Deterministic Policy Gradient, or DDPG for short. As can be seen in the plots, BDQ performs competitively against DDPG. Remarkably, on the most challenging domain in our experiments, the OpenAI's humanoid domain, BDQ in purple and blue significantly outperforms DDPG in orange. The humanoid domain involves 17 action dimensions, which leads to a combinatorial action space of approximately 6.5 times 10 to the 25 possible actions for the discretization case with 33 discrete sub-actions per joint. To perform competitively against the state-of-the-art continuous control algorithm in such high-dimensional domains is a feat previously considered intractable for discrete-action algorithms. To summarize, we introduced a novel neural network architecture called action branching that distributes the representation of the policy or the value function over several network branches, meanwhile maintaining a shared network module. We hypothesized that this shared network module can potentially enable a form of implicit centralized coordination for the distributed branches. We designed a novel agent by adapting the DQN algorithm along with several of its well-established extensions into the proposed action branching architecture. We illustrated empirically the effectiveness of the proposed architecture in enabling the application of a currently restricted discrete action algorithm to domains with high-dimensional discrete or continuous action spaces and verified our hypothesis. Finally, we believe that the promising performance of the action branching architecture in a scaling DQN hints at its potential generality and thus its application to other discrete action algorithms. We have released the code for BDQ on GitHub, which can be accessed online at the link provided. For any questions regarding this work, you may reach me by email or via Twitter using the details provided on this slide. Thank you for your attention.